So Hilbert space is also an important class of infinite dimensional Banach spaces. So Hilbert space is a nonlinear space where each norm is generated using a inner product. So we know the properties of inner product. That is inner product x comma is greater than or equal to 0. It is equal to 0 if only if x equal to 0, and inner product is also linear in one argument. Inner product x plus y comma z equal to inner product x comma z plus y inner product y comma z, and inner product alpha x comma y is equal to alpha into inner product of x comma y, and inner product of x comma y is equal to inner product of y comma x bar, where x y z is in x and alpha belongs to k. If the scalar field, the vector space of scalars k is equal to R, then the last property would be inner product x comma y inner product y comma x. Then x is called the inner product space. So if in a vector space we can define a function like this, it is called inner product space, and if k equal to R, then x is called a real inner product space. So this is the properties of inner product space. Every inner product gives rise to a norm. So using every inner product we can construct a norm, and a complete inner product space is called a Hilbert space. So we can define norm on every inner product space by norm of x equal to inner product of x comma x taken the square root. For example, we can consider r power n. We can define inner product in r power n by inner product x comma y equal to summation I equal to 1 to n xi yi. Then inner product x comma y is an inner product, and if you take inner product x comma x whole power 1 by 2, then we can say that it is nothing but our 2 norm we have defined in r power n. So 2 norm in r power n can be generated by an inner product, and the property is that only 2 norm can be generated from an inner product. No other p norm in r power n can be generated from an inner product. Since r power n is complete, r power n with respect to 2 norm is called a Hilbert space, because a complete inner product space is called a Hilbert space. So inner product vector space, if it is complete, we call it the Hilbert space, and since we already know r power n is complete, we have r power n is a Hilbert space. It is also called Euclidean space. So r power n over 2 norm is a Hilbert space, and any other norm it need not be a Hilbert space, because for any other norm that norm need not be generated from a inner product. That is, for any other norm we cannot find a inner product which generates a norm by inner product x comma x is equal to norm x square. Consider L2 over R, the set of all real sequences that are square summable, and in L2 over R we can define inner product as inner product x comma y equal to summation I equal to 1 to infinity xi yi, and this will be an inner product, and this will generate the 2 norm. If it is a if L2 is a vector space over a complex field, then we can define inner product as inner product x comma y equal to summation xi yi bar. So this inner product will define the 2 norm of x equal to inner product x comma x raised to the power of 1 by 2, which is equal to summation I equal to 1 to infinity xi square to the power of 1 by 2. So L2 is a Hilbert space. Similarly, we can see that C of AB with respect to 2 norm is an inner product space with inner product f comma g equal to integral a to b f of x g of x bar. So if it is over a complex field, then we can define as integral f of x g of x bar. If it is a real field, we can just define inner product integral f of x g of x. So C of AB with respect to 2 norm is an inner product space. But we have already seen that C of AB with respect to 2 norm is not a complete metric space which is generated from this norm 2 norm. Therefore, C of AB is inner product space, but it is not a Hilbert space. So C of AB with respect to 2 norm is an example of inner product space, but not a Hilbert space, because only a complete inner product space can be a Hilbert space. Also, capital L2 of A comma B. Capital L2 of A comma B is a Hilbert space with a similar inner product F comma G equal to integral over Lebesgue integral over closed A comma B F G bar d mu, where mu is the Lebesgue outer measure on closed interval A comma B. And here capital L2 of A comma B is a Hilbert space because it is a complete nonlinear space, and also we know that capital L2 of AB is a completion of C of A comma B. So what distinguishes this inner Hilbert space or inner product space? We can observe that every inner product space satisfies parallelogram identity, because we can write norm x square as norm x square equal to inner product x comma x. Therefore, we can easily check that every inner product will satisfy the parallelogram identity, that is norm of x plus y square plus norm of x minus y square equal to 2 into norm of x square plus norm of y square. So this is the inequality which every inner product should satisfy, and the norm which arising out of the inner product should satisfy this inequality. And it is also the necessary condition for a non-linear space to be the inner product space. So this is not only a equality satisfied by inner product space, but if a norm, if it has to be an inner product, that is, if a norm, if it has to be generated from an inner product, then that norm should satisfy this parallelogram identity. So a non-linear space is inner product space if and only if it satisfies the parallelogram identity. And we can show that LP is not an inner product space for P not equal to 2. That is, for P not equal to 2, we can show that LP does not satisfy the parallelogram identity. This we can do by taking any two elements xy in LP such that it does not satisfy parallelogram identity. So thus we can easily find any two elements in LP, suitable elements such that it does not satisfy the parallelogram identity. Similarly, R power n with respect to P norm, C of AB with respect to P norm, LP with respect to P norm, they will not be inner product space for P not equal to 2. So we can see that among all the norms, P equal to 2 holds a special place, because only for P equal to 2 a non-linear space can be a inner product space. So if P not equal to, then none of the above vector spaces R power and C of AB and LP can be a inner product space. If X is a real inner product space, then inner product x comma y is equal to 1 by 4 norm of x plus y the whole square minus x minus y the whole square. So this is a relation between an inner product and a norm. We know how to get a norm from the inner product, norm x square equal to inner product x comma x. So how to get the inner product from the norm? But this can be done only within the inner product space. So otherwise this will not be a inner product. Only in inner product space this inner product x comma y satisfies all the equalities of the inner product. And also every inner product satisfies the Schwarz inequality, that is modulus of inner product x comma y less than equal to norm x into norm y. So this is the Schwarz inequality which is satisfied for all the inner products. And also another interesting property is, if xn converges to x and yn converges to y, this implies xn yn converges to x comma y. So the inner product is continuous simultaneously with respect to both the arguments. If xn converges to x and yn converges to y, then xn comma yn converges to x comma y. If inner product x comma y equal to 0, then we say x is orthogonal to y or x is perpendicular to y. So we can understand this inner product shares a lot of properties similar to the dot product we see in the vector analysis. In vector analysis we define dot product and we define a and b to be perpendicular if a dot b equal to 0. So this inner product shares lot of properties with respect to the dot product. For any two subsets a, b of capital X, a is perpendicular to b if a small a perpendicular to small b for all small a belonging to a and all small b belonging to capital B. So here we have the notion of when two sets are perpendicular. Two sets should be perpendicular if we take any element of one set and it is perpendicular to any other element of the other set. And also if x is perpendicular to y, this will imply that norm of x plus y square is equal to norm x square plus norm y square. Because if x is perpendicular to y, then inner product x comma y equal to 0. So here we can see that norm of x plus y square equal to norm of x square plus norm of y square. This identity is also called Pythagorean identity or Pythagorean theorem, because it says that the hypotenuse is nothing but the sum of the squares of the other two sides. And also another property of the inner product is if inner product x comma u is equal to inner product x comma v for all x, then u equal to v. So inner product, if you fix one element, then it also defines a function. That is, if inner product x comma u equal to inner product x comma v for all x, for all x this is true, then we can be sure that u equal to v. And also another interesting property of this inner product is if norm xn converges to norm x and inner product x comma xn converges to x comma x, this will imply xn converges to x. Because we know that xn converges to x implies norm xn converges to norm x, but the converse need not be true. That is, norm xn converges to norm x need not imply xn converges to x. But in addition, if inner product x comma xn converges to inner product x comma x, then this will imply that xn converges to x. If elements of a subset are pairwise orthogonal, then it is called a orthogonal set. If we take any subset of an inner product space, it may be finite or infinite. If we take any two elements of the set and if they are perpendicular to each other, then we say that the whole set is a orthogonal set. In addition, if each element has norm 1, then it is called a orthonormal set. So an orthonormal set is a set where any two elements are perpendicular to each other and also each element has norm 1. So orthonormal set has a special role in Hilbert space, because using orthonormal set we can generate a suitable basis for the Hilbert space.